Great. Yes, I'm going to talk about chronic Neuropixels recordings. As Julia just said, there are two ways of going, acute and chronic. But maybe before I start, I just wanted to say that most of the things that Julia said are going to be exactly the same with chronic, and mainly about like the quality of the craniotomy you need to have, sharpening the probes and so on. So all these aspects, bear in mind that you will have to, the tips that she gave are almost exactly the same for the chronic. So here I'm going to specifically talk about, the specifics of the chronic neuropixels. All right. So yeah, just the outline is pretty simple. I'm first going to tell you a bit about why you may want to do chronics. There are some obvious things. The first one is if you want to record from freely moving animals. So, the probe is going to be cemented somehow to the skull of the animal. It's going to move with it. So, the animal can move around and you're going to record stably the same neurons. It can also be because you want to track neurons across days if you're interested in learning or memory or some processes like that. So this is an example here where, the same neuron is being recorded for different days and you can see its responses to different images is stable across days in that case. So that's how we can recognize also it's the same neuron. Another way, another interest for that is that you can actually record from the whole probe while minimizing setup time. So if these are, this is a 4-shank Neuropixels 2.0 inserted into the brain, you can start recording the top of the brain, and then the next day, the part just below, and so on and so forth, so that you tile the whole of the portion of the brain you're recording from. And on each of those, you can run your own experiment. Okay. And finally, there are some other advantages that you may not have thought of initially, but that you can record brain activity across contexts. So that means you can put the same mouse and record from the same neuron, put it into the freely moving or head fixed, or in one rig or another. And you can also share mice across experimenters, which we do here in the lab. The main two principles are actually either using permanent implant or reusable implant. The first one is you cement the probe directly to the skull, and it's usually you can't recover it or it's pretty hard. The second one is you use a device that I'm going to go through to actually recover the probe after that. Okay, so let me first talk about the permanent implant. The way it goes is you insert the probe into the brain. I'm not going to go into the details. I'm just using a schematics here where this is the probe, this is the shank, and it's going into the brain. Here's the frontal part of the mouse brain. But basically everything that Julia said applies here too. So you have to pay particular attention to the quality of the craniotomy. You have to go down slowly, sharpen your probe before that, go down slowly, make sure there's no bleeding, so on and so forth. Okay, so it's just like an acute recording. But once you've reached the target area, what you do is you cement it to the skull. Okay, so you're going to apply cement. Sometimes you can put a bit of Vaseline on the shank before that, or there are different tricks. But the principle is you cement the whole thing to the skull. You can cover it with a protector so that, when the mouse is moving around in its cage, it won't damage the probe. And finally, for explantation, there is, the only way is to drill it out. Some people manage to do it, but it's, it's not the main advantage of that process to reuse the probe. The second principle is to use reusable implants, and this is what I've been mainly working on. So, that's the part I'm going to take a bit more time on. But basically, you have the probe here, and you use the general principle is you have two types of modules, which I'm going to call the payload module and the docking module. The way it goes, so these guys can have like many different shapes, and I'm going to go through it afterwards. But the way you go is you attach the payload module, the probe to the payload module, okay? And then you assemble the payload module, which is attached, like physically cemented to the probe, to the docking module. And then you go again into the brain, okay? So then you do the same thing as what we just saw before. These two parts, the payload and the docking module, are securely attached to each other through screws or some other devices. And then what you do is you cement the docking module to the skull, okay? So the payload module and the probe do not have cement attached to them. It's only the docking module. And once you're done with your experiment, you can record for months, whatever you want. You can explant the probe, and usually you come with an external device. You attach it to the payload holder, to the payload module, sorry. And then you detach the payload module from the docking module. Okay, so if it screws, you will just unscrew that, and then you retract the payload module. Okay, so that means that this part here is the precious part, and that's the part you can reuse across experiments. That part here, the docking module, is lost more or less, but in most of the devices, it's actually something that costs like a few pounds. Okay, so that was for the surgery part. I gave you the general principle, but now it comes in many different flavors. I won't go into the details of those. I've put here the main references that I know. There may be some more now in 2025. Some of these papers are actually published in 2025 now. They were preprints at the time. But you know, the main principle is always that you have the probe, it's attached to this the payload module, and the docking module is cemented to the skull. And you know, the same principle applies. Now, sorry, I'm going to focus on this one, which I've designed with Philip Cohen, not because it's the best, but because that's the one I'm most familiar with. But in general, what you want, if you want to pick one of these devices, what you want to look for, or the questions you want to ask are the following. At least that's the one I think of when I choose a chronic implant. The first one is which brain area you want to target. And by that, I mean, do you have any specific constraint on the angle you will use? What's the maximum weight that you're allowed to use? In the UK, for example, we usually have limitations on how much weight we can put on the head of the mouse in our case. How long do you want to record for? What's the level of flexibility you need? Do you want one probe, two probes? Do they have the same angle or not? And so on and so forth. So there's a variety of questions that and each of the different implants usually fits for a specific set of answers to these questions. So I've put here a large table with the different implants that I know and different types of things that they've been tested in. So some of them have been tested in mice or rat or both. The different brain areas they've been tested in, which Neuropixels version, how many probes you can have. Usually it's 1 and up to 4, sometimes up to 6 when you have not that much limitation on weight. You also have the weight that these implants weigh. It's not always clear from the publications how much weight it is, so you may want to try it yourself, and then different features. Okay, and these slides will be available on. Now I'm just going to overview some of the results of all of these different implants through different categories. The first one is the stability. So for how long can you record neurons with these chronic setups? And these are from all the different papers. It's always the same kind of graph. I'm going to take you through the first one. This is usually on the x-axis, the days post-surgery, okay? And on the y-axis is the number of isolated units. And it can be isolated units, neurons, depends a bit on the paper. And here you can see that these are the different mice. Each line is a different mouse. And usually you can see that at the beginning there may be some drop-off. It's particularly clear here in this paper. So there is a drop of units and then it stabilizes. To be honest, in my own experience, this shape can vary a lot depending on the mouse, depending on the surgery. It's very hard to understand what is driving like a good implantation versus not. Definitely surgery quality is one factor. But sometimes you can start with very few neurons and then they appear. Sometimes it's stable throughout, like these recordings. You can record for a very long time, like these ones. So it varies a lot depending on the implant, but I would say that the inter-implant variability is overwhelmed by the inter-mouse variability. Usually it's very variable across animals. So stability here, we were just counting the number of neurons. You can also, oops, sorry, these are just the conclusions. You can also try to track the neurons, and Annie is going to talk about it actually, on how to do it. This is a slightly harder thing to do, but here is an example where we tracked here for about 100 days a population of neurons. This was in frontal cortex, and you can use the waveforms of these neurons to track them and check with some functional measures that they are indeed stable. But Annie is going to go into depth about it. But what I want to emphasize here is the probability of tracking neurons across days, even if your implants are quite stable, usually decreases over time. Okay, so you may resample the population of neurons that you have around the probe, and it can be pretty hard to track neurons across days. Okay, it's still doable, and after here 100 days, in some cases we still had like a 0.2 probability of tracking the same neurons. It will depend on the setup you use. But that's just something I wanted to flag. Another thing is the reusability. So you can, as I was mentioning at the beginning, these reusable implants, you can implant them once, take out the probe, reuse again in a different mouse. And there are some different papers trying to quantify how much this was impacting the quality of the results. And overall, there's no impact. So here on the x-axis is the number of probe uses, and on the y-axis are the number of units that were recorded, how fast they were decreasing, or the overall noise. And you can see it's pretty stable. It does not depend on how many times the probe was used. The same for these other papers that also quantify this. So that's something you may want to look into if you're interested in really reusing the probes a lot. Another thing that can be pretty important is all of these different devices have been designed by different labs, sometimes on their own. But one pretty important thing is to understand how easy it is to use and how reproducible it is. And there are some papers that actually quantify this. I won't go into the details, but this paper actually tested it in 10 different labs independently. And they quantified whether the fact that the person using it was trained directly or not had an importance. And overall, this was very reproducible. And it's the same thing that we had in our lab, where each color here is from a different lab and the quality of the recordings were the same, even though actually these people were mostly not even trained by us when we designed the implant. Okay, so that's something that you may want to look into, is whether it's transferable to other labs. And finally, you may want to wonder about the flexibility. And here in our lab, we designed the implant for 1.0, 2.0 probes with or without a head stage. A miniature version, if you want to implant just one probe, the initial one is designed for 2 probes. If you want a bigger species, if you like rats, you may want to have an encasing around it. And you may want to control the angle or the distance between the 2 probes in that case. And some implants are actually pretty good for that, especially for the angle between probes. And you can implant different probes with different angles. Okay, so and usually one of the features that I find pretty interesting is for these implants that are 3D printed and that everyone can modify. And actually in our GitHub place, people upload the modifications they've made, so it's kind of a community-driven thing. All right, and all of this, finally, that's another thing you may be interested in, is whether you can use them for freely moving. So, all of these different types, they can be used freely moving. Most implants actually don't really impact the behavior of the mouse. This is just the trajectory of the mouse in an arena before and after implantation. It's barely impacted. And some people actually use specific devices like pulleys and so on to relieve from the weight. And it's been also tested in, when several mice are in the arena. All right. Just a few challenges. I see that I don't have much time, but basically, just to wrap up, the main challenges are stability. It may depend a lot on the brain regions. For example, in our case, we find that superior colliculus, which is very much at the back of the brain, is very hard to hold neurons from. Tracking the exact same neurons can also turn out to be difficult, even though you keep a good population of neurons overall. The weight and size, it's very hard to get below 2 grams, although I do believe that the fact that the probes are becoming smaller and smaller is going to help. And also the flexibility, that's something that is really going to constrain which implant you want to look for. All right, and finally the robustness, but that depends a lot on the species you use. Okay, so just to wrap up, I think overall this is a very expanding field. Keep an eye on the new papers and the new implants, or even old implants, but that may have some updates. Think a lot about which implant you want to choose. It depends a lot on your needs and the questions you may have. And you may find also useful to try to address these challenges by designing new implants yourself or updating already existing ones. The main one being the stability, the size, the flexibility, and the robustness. And with that, I just want to thank you for your attention.